Now we're going to go a little deeper into that electric current, and we're going to talk about resistance and how we work with current and resistance. All right, so what is resistance? Well, resistance is exactly what it sounds like. It's an oppositional action. So, electrical resistance is the opposition to the flow of an electrical current, and this opposition obviously is going to produce some heat. When you oppose the current's flow, we're going to produce some heat. Um, when you have a greater resistance, then you get less current flowing through it. Good conductors are going to have a low resistance because you want a greater flow, you want greater current. Okay, we measure electronic resistance in ohms. Measure it in ohms. This is a great example. Here you have something of obviously low resistance. This is the symbol for ohms. It is the Greek letter omega, which is not necessarily for you to remember. But here you have 1 ohm of resistance, which allows for a large flow. You can see that. Here you have 2 ohms, which is allowing for a much smaller flow. This is a very basic illustration to show exactly, show that flow of electric current. Okay, 1 ohm, low resistance, 2 ohms, a little bit higher resistance, showing the difference in that flow of current measured in ohms. Very important. All right, so there's 4 basic things we're going to talk about that influence resistance. The material of the wire that we are using for our circuit. Aluminum and copper, they have very low resistance. They are used quite often in wiring. So the kind of material is obviously going to influence resistance. The thickness of that material, the thicker the wire, the lower the resistance. So if you have a rather thick wire, you're going to clearly allow more electric current to flow through that. It's very logical. If you have a larger place for something to go through, it's going to go through much easier. So a thicker wire is going to give you a lower resistance. Remember, we want lower resistance. It allows that current to flow more easily. The length of the wire. If a shorter wire is going to have lower resistance, you have less stuff that is in the way of the current. So if there's less stuff in the way, then that allows that current to flow better. So the farther that wire is stretched out, the more difficult it will be for that current to travel along it. And the temperature. Lower temperatures generally have lower resistance. Now, at first, you might think, well, that's kind of weird. I think that if something's warmer, the higher the temperature, the more quickly the atoms move. And that is true. However, because of that higher temperature, because of that movement of the atoms, you also remember that those atoms are crashing into each other more often. So if electrons are bumping into each other more often, then they are not flowing as often. Kind of like changing classes in the hallway. The more students that get in there, the more congested it is, the less likely they are to move. So too much stuff moving around much faster, going to bump into each other more often, right? And it's going to slow down the flow. So lower temperatures, everything's moving more slowly, but it's moving along better. So let's talk about some important terms. First of all, voltage. Voltage, that's the measurement of the energy given to the charge flowing in a circuit. Okay, so how much energy is that charge flowing in the circuit, right? Voltage has a lot to do with the force or the pressure that drives that current through a circuit. So a greater voltage is a greater force of the flow of those electrons. So we remember that in nature, things tend to go from areas of high concentration to areas of low concentration. Electrons flow from areas of high potential energy to areas of low potential energy. Remember, potential being that collection of charges. So higher charges, if you have a higher collection of charge, they're gonna flow to an area of a lower collection of charge. Much like lightning discharging from a cloud. If you get a large charge build up, it's going to flow to an area of less charge. Um, the difference in potential that causes the flow, that's what we call voltage. That difference in potential is what we call voltage. So a greater difference is going to cause that flow to happen with more force. So if you have a really, really high concentration on one end and a very, very low concentration on one end, that current is going to flow with a lot of force. But if they're more even, then it's going to flow with a little bit of force, not as much force. Current, electric current, we talk about electric current, right? It is the rate at which charges pass through a given point. So it's the rate at which the charges are flowing, right? We like to measure things in rates, tell how long it takes something to do something, how long it takes it to flow. So current is the rate at which charges are passing through a given point. And you often see this measured on your home because we like to measure the rate at which we use that electricity so that the wonderful electric company can charge us for the electricity we are using. We measure current in amperes, often talked about in amps. We shorten that a little bit. So the difference between volts and amps, right? We're both talking about the electric current, right? We're talking about how fast it's flowing, right? And we're talking about the force that it's flowing with, right? So how much are we using? That's our amps. And what force is it flowing with, right? So if you are measuring a water hose, right, the amps tell you how much water's coming out. The volts tell you the force that they're coming out. So when you cover the tip of that hose with your thumb and just let that same amount of water's coming out, but it's coming out with so much more force, right? That's how you might hose something off. So same amount of water, it's just coming out with a much greater force. Okay, so the amount of power, right? Remember power, that's how we can do work, right? The amount of power you get from electricity is a function relating the force to the amps. Okay, your power is the voltage, once again, that's the force, times the amps, right? So that's your power. Power measured in watts, right? Volts times amps. Watts equals volts times amps. It's basically the total. It's a function of that relationship. Power equals volts times the current, or watts, which is what we measure power in, volts times amps. Now Ohm's Law, very important, especially if you are ever going to wire stereo systems in your car. Everybody wants a good system in their car, so you want to know about Ohm's Law, because this helps us to relate, once again, voltage, resistance, and current, right? Resistance, very important. High resistance, you're going to have trouble transferring that power. So it's yet another function. The current, right? That's the amps. How much is flowing through? That is equal to the voltage divided by the resistance. Seems logical, right? A greater resistance, it's going to end up lowering what you have flowing. And voltage, once again, that's the power, the force with which it flows. So current, which is measured in amps, is equal to voltage divided by ohms, or we might refer to this as ohmage. Voltage, ohmage, it is a function. The amount of current you're going to get is equal to the power, the force with which it is flowing, divided by the resistance, what's holding it back. And also, it's often referred to, since it's Ohm's Law, you can refer to it as ohms, or ohmage, is equal to the voltage divided by the amps. The voltage, once again, that force, divided by how much. That is going to give you your level of resistance. All right. That was very basic version of volts and amps, ohms, all the different things that go into resistance, current, and the force of electric current.